Hey guys, Kevin here, back with another AIME question. This time it is the 2003 AIME 1 number 6. We see here that it is a geometry question. So the sum of the areas of all triangles whose vertices are also vertices of a 1 by 1 by 1 cube is some value, and we want to find this value. Okay. So when starting on this question, it's always nice to be sure of what we're looking for. So it says sum of the areas of all triangles. Does this mean we are summing over all possible areas or all possible triangles? And based on which one it's asking, we will arrive at different answers. And if you misinterpret this question, then you're likely to get it wrong. So in this case, it says the sum of the areas of all triangles. So all triangles is the key here, because basically we're finding all triangles that satisfy this condition and then taking the areas and summing them. So in this case, we're summing over areas of all possible triangles. Okay, so let's get started. For this type of stuff, we just want to find out the different configurations that the triangles can be and what areas they represent, and just sum them. So this is a good problem to use casework on. And on all instances of casework, we're gonna start by fixing some value, which is we're gonna fix the two starting vertices. So where can the two starting vertices be? Well, let's suppose that two vertices lie on an edge. And we're gonna first do this case because it's rather easy to imagine. You have a cube and we're taking an edge, and the two vertices will be the vertices of that edge. So where can the last vertex go? Well, there are 6 positions, 6 remaining positions. And 2 of the 6 are on the edge diagonally opposite of the initial edge, because if we have an edge in the cube, then there's a diagonal edge, basically the edge obtained by just reflecting the edge over the center of the cube. Kind of complicated but basically, if you imagine a cube, there's going to be an edge that's farthest away from any edge in terms of distance. So that's going to be the opposite edge. And 4 of the 6 are going to be are on a side that are on 4 of the 6 share a side with the edge. So 4 of the 6 share a side with our initial edge, while 2 of the 6 don't. And of course, if you want to kind of see the logic behind that, it's basically you can just draw a diagram, and that will really help in this question where it's very hard to imagine 3D figures. So let's do our first case. 2 vertices lie on an edge. Other vertex is on diagonally opposite edge. How many triangles does that give us? Well, if two vertices are on an edge and the other vertex is on a diagonally opposite edge, then we don't really need to worry about permutations or anything. We can just pick an edge, and then we can pick one of the two cases that are diagonally opposite. So there are two possibilities for every single edge, and there are 12 edges, so there are 24 triangles. And with area, let's not calculate area first. You know the side lengths instead. Because two vertices lie on an edge, then one of them has to be 1. The other vertex is on the diagonally opposite edge, so here's where a diagram really helps. Because when you draw a good diagram, then you can see that our last vertex will share a side with one of the two vertices. And this gives us our distances of root 2 and root 3, because it will be diagonally opposite to the other vertex. And we can use herons, or notice that this is a right triangle, so the area is root 2 over 2. And this case contributes an area of 12 root 2. So case 2 now. Two vertices lie on an edge, other vertex is on a shared side edge. Oh, not edge. Shared side. So this means that all three vertices lie on a side. So the area is 1/2. And how many triangles are there? Well, we can pick any of the 6 faces, and then there are 4 ways to choose a triangle on that face by just constructing a right triangle and then rotating it around. So there are 24 triangles, and this contributes an area of 12. So these two cases combined establish the general case of when two vertices lie on an edge. So our remaining case are to deal with when no two vertices lie on an edge. And this is a very nice condition because it means we can eliminate vertices from being ones that we want. So basically we've narrowed it down. So how can this happen? Well, let's just pick any vertex. There are 7 positions for the second vertex, but 3 of them are unavailable because they are adjacent to the first vertex. And that means that they share an edge. So we have only 4 possible locations. And what are these 4 possible locations? Once again, please draw a diagram for this question. Basically, if we pick any vertex and then scratch out the vertices that are directly adjacent, then the remaining vertices, 3 of the remaining vertices will share a side with the vertex. But they won't be sharing an edge, which means they're on the diagonal of that side actually. They're diagonally opposite from that side. While the last one is diagonally opposite. So this is the one that's as far away from the first vertex as possible. So this gives us our two nice cases. So case 3, no two vertices lie on an edge, and last one, and basically our first case, and two of them share a side. This isn't a very rigorous case, I know, but basically it's the first case in the three of the remaining cases. The three of the remaining vertices will share a side with the vertex. So basically this is the second vertex. So let's try to find out where the last vertex is. Where is the last vertex? 6 remaining positions, and of course with a good diagram we can also cross out. So just pick any of the 3 random locations for the second vertex and then see where it can go. And there, of the 6 remaining positions, 3 plus 3, so these are the ones that are adjacent to one of the 2 vertices, but -2 for overlap because they share a side, and thus they share a side with 2 other vertices as well. So 4 of these are unavailable, so there are only 2 positions. And where are these 2 positions? Well, they form a nice sort of symmetry with the other 2. And this gives us, it's really easy to see this if you draw a diagram. So yeah, hint hint. Equilateral triangles with side length √2. And how many of these are there? Basically, these triangles are when every single side of this triangle will be a diagonal of one of the faces of the cube. So how many are there? Well, let's just pick I mean, we can just count all of them. There shouldn't be too many, but if we really wanted to brute force it, I guess, if we fix one diagonal, then we found that there are only 2 triangles that result. Therefore, since there are how many diagonals? Well, there are 6 faces with 2 diagonals each, so there are 12 diagonals. So there are 12 times 2, and you may think it's 24 triangles, but in actuality we overcount here, because since each side of the triangle lies on the diagonal of a face of the cube, then basically we can kind of rotate the triangle in order to get the same triangle, but we count it multiple times in what we do here. So we can imagine this count, 12 times 2, to be basically we're going over all possible diagonals and then taking the 2 triangles that result. While because if we rotate it, then the triangle, then it stays the same, but basically our initial diagonal is shifted to another face, which is then overcounted. So this is overcounted for every single possible rotation, which gives us a total of 8 triangles. With area, and of course, area of the equilateral triangle is not hard to compute. This gives us √3 over 2, contributing an area of 4√3. In our last case, no two vertices lie on an edge and two are diagonally opposite. So let's draw a diagram. If we have two that are diagonally opposite of the 6 remaining vertices, how many are possible? Well, in actuality, basically none of them are available because all of the 6 remaining vertices will be adjacent to one of the 2 vertices. And of course, you can just test this out by drawing a diagram. Of course, this wouldn't really hold up, and if you were trying to prove this, in which case you can do some fancy argument by saying like how the two diagonally opposite vertices are a taxicab distance of 3 away or something. And basically, of the 6 remaining vertices, none are available. So there are no triangles. And summing, we get a total area of 12√2 plus 12 plus 4√3. What was our answer format? M plus √m plus √p. So let's convert that. So this is 144 times 2, 288, plus 16 times 3, 48. Gives us an answer of, we're supposed to sum those, right? 348. And that is it.